Hello and welcome to our lightning talk about our new processor in memory design, which we title pPIM, a programmable processor in memory architecture with precision scaling for deep learning. This work is recently published in IEEE Computer Architecture Letter. So the reason of designing a processor in memory is because of the so-called proverbial memory wall, or the highly power-hungry and latency-intensive processor to memory interconnects. In a unique way, we adopt lookup table-based processing to provide functional programmability and flexibility in the processing so that we can dynamically update our algorithms in the processor as well as adapt the processor for different suites and classes of applications. In particular, in this work, we have focused on deep learning suite of applications such as convolutional neural networks or deep neural networks. We also demonstrate that our processor in memory is capable of operating on 8-bit precision inputs as well as reduced precision 4-bit data depending on the mode of operation that we choose, resulting in varied performance metrics with a trade-off towards functional accuracy for the deep learning class.
Our architecture takes a hierarchical design where we have 9 of our processing elements that we refer to as cores and combines them together into an overall cluster. Within this cluster, each of the cores are able to communicate with each other, where the output of one core is then shared with each of the other cores as well as itself. Within our PIM core combines 8 256 to 1 muxes so that we're able to perform 4-bit operations, or we're able to perform a 4-bit multiplication on 2 4-bit inputs, A and B.
For performing the operations, we basically first decompose the operands and distribute them across multiple cores via the router, and then perform the operations in multiple stages across the LUT cores. And in this way, we are actually able to obtain 2 operation modes: the 8-bit operation, where we can perform 8-bit max, and the MAC means multiplication and accumulation, and the other one is the 4-bit MAC. Now, for performance evaluation, we are actually capable of implementing the CNN, DNN, convolutional, fully connected, polling, and activation layers. And for these all these layers of CNN, DNN, we are comparing the throughput and power of our device with other CPUs, GPUs, and other PIM accelerators. And we can show from this comparison that our device is able to obtain low power consumption, scalable comparable throughput, and also 1.46 times performance per unit power compared to another comparing LUT-based architecture called LACC.
For performance evaluation, we have done for throughput and energy per frame, comparison between 8-bit and 4-bit inferences for various CNN algorithms is shown in the plot 1. And in the plot 2, we observe negligible loss of accuracies with precision scaling. And we observe 2 times throughput and 1.3 times energy efficiency with 4-bit inferences compared to the baseline.
To conclude, in this presentation, we have spoken about our programmable processor in memory, which offers higher superior performance with better energy efficiency compared to state-of-the-art CPUs, GPUs, and other PIM-based accelerators.
Thank you very much for listening to our presentation today. Hope you have a good day.